Sorry. Thank you very much for the kind introduction. I hope you can all hear me now. I have a new machine, so sorry for the technical issues. So what I would like to talk about today is structured ML training via conditional gradients. And that's going to be a bit of an advertisement type of talk for conditional gradient methods. And yeah, so what's this talk going to be about? This talk is going to be about a lot about sparsity, a bit about deep learning, and we will also have some combinatorial optimization aspects here, however, mostly in passing. And as the title indicated, there will be lots of conditional gradients. So what's the underlying idea? It's actually a very simple idea, namely that we can use combinatorial polytopes, say chi-sparse polytopes or LP balls, to in some sense regularize our learning problem that we might face in machine learning. And we can use this to induce solution structure and sparsity. So today I want to keep it like on a very high level, just to give you guys a bit of an idea what can be done in that space and present two examples where we have used this in the past. And what I will do is I will give a very quick recall on what conditional gradients or Frank Wolf-like methods are about. Then I will talk about one example where we learn dynamics via conditional gradients. And then we will use conditional gradients in the context of training deep neural networks. So let's get started. Just a very quick reminder that so all the references here in the talk are hyperlinked, and if you have the PDF later, you can click on them, and they're certainly not going to be exhaustive, so please check the references contained therein. So let's start with a recap. So the problem that we would like to solve is very simple. We want to minimize a smooth and convex function f over a feasible region, and typically we would consider polytopes p here. And that's the optimization problem that we would like to solve. As you can imagine, this is a very versatile model, and you might know many different applications. And in this context, you can model information about both the function f and the feasible region p in different ways. These methods tend to work really well also in real-world applications. And you could say that arguably, at almost all learning algorithms in one way or another use some form of loss function minimization to model some type of a learning problem. So the model that we are going to use here today is the following. We will assume that we have access to the feasible region P by means of a so-called linear optimization oracle. That means given a linear objective function C, this oracle will return the linear minimizer over the feasible region with respect to that linear objective. And for the function f, we will assume first order access. That means that given a point x, we can obtain gradient information as well as function evaluations of our function. In particular, that means if we talk about any form of complexity here, this is all relative to these two oracles, of course. Good. So now let's talk about specifically the Frank Wolf algorithm or conditional gradients as a way of doing that. So you see the algorithm on the left, but rather than looking at the algorithm, I think it's easier to look at the figure here. So we start out with some initial iterate or some iterate, let's call it xt. And then what we would do is we compute the negative of the gradient. And if you would do gradient descent, you would follow this direction now. But here you do something slightly different to use this gradient to actually minimize that gradient over your feasible region. That will give you a vertex vt here. And then rather following the direction of descent from the gradient, you take a replacement direction formed between xt and vt, and you follow that line segment. And you can then do some form of line search or have some step size rule in terms of how far you move on that line. And then you basically can stop once you have converged, and there's all types of stopping criteria and so on and so forth. What are a couple of advantages of these methods? First of all, as you can see from the algorithm, they're extremely simple and robust. There's no data structures. You just form convex combinations. And as long as you have these two oracles, they're extremely easy to implement. What is more important from an optimization perspective and for many applications is that these algorithms are projection free. And what this refers to is the fact that if you would do gradient descent over a constrained feasible region, then you would have to project back into the feasible region. And that typically amounts to an optimization problem itself that can be quite hard to solve. Here, on the other hand, we always form these convex combinations, so you stay feasible all the time, and here there's no need to project back. And that can be a huge advantage in many applications. But more importantly for us today will be the next 2 points on my list, namely that these conditional gradient algorithms have an implicit bias towards sparsity. And what I mean by this is that you build up your solutions, your iterates, as convex combinations of vertices. So you know, for example, that after t iterations, you have picked up at most t of these vertices. And then also, if you think of how the updates work, we follow the line segment between the iterate and the vertex. So if the vertex has a specific structure, you actually perform structured updates on your iterates, which can be very useful to induce sparsity or other forms of structure. Yeah, so that's on the advantages side. There's also disadvantages. In particular, the convergence rate is only 1/t, whereas with accelerated gradient descent, you can get 1/t squared. There's a fundamental barrier to this, and there's many good reasons why you cannot do better than the 1/t, but that's beyond the scope. And also effectively in real-world applications, this theoretically suboptimal rate doesn't really matter at all, because you have all types of other structural inducing properties such as sharpness or Hölder error bounds that give you improved convergence rates anyways. Yeah, so that's basically the Frank-Wolf algorithm in a nutshell. Let me very quickly convince you guys of a convergence of 1/t. So suppose you have an L-smooth function f and a polytope p with a diameter d and a step size rule, which is basically 1/t. Then the primal gap, which is what is written here, contracts basically as O of 1/t. And the proof is very simple, and all these proofs somehow work very similarly. There's typically just minor modifications depending on the structure that you have. So you look at the improvement per round. So this is a negative of the improvement of 2 iterates. And that you can directly upper bound by the smoothness inequality. And what smoothness really means is just that the gradients don't go crazy, or put differently, at every point on the function, you can fit a quadratic on top. And that's the quadratic that is written here. And then you just plug in the definition of how your iterates were defined, and then you can rewrite this in the way of how it's done here on the right. So there's really nothing special happening here. And now you use the properties of the algorithm, namely that the VT was a minimizer, so that you know that this inner product with the gradient is lower bounding the inner product with the optimal solution x star here, and that by convexity lower bounds minus of the primal gap. And on the other hand, you have that the diameter of P was bounded by D. Now you just put everything together and you get a contraction. And now this contraction basically tells you how the function value is contracting, the primal gap is contracting, and whenever you have a formula of that form, there are standard ways of deriving a convergence rate, and you just plug things in and you get your 1/t rate. So that's basically how you show that this algorithm converges at a rate of 1/t. Yeah, so that's basically that. There has been significant progress over the recent years in that context. We don't have the time to go through all of that. Let me just say that with all these improvements and special cases, conditional gradients have become very competitive. They're extremely simple and robust, and typically perform extremely well in real-world settings, in particular if you have more complicated constraints where projection onto the feasible region is non-trivial. And there's also an upcoming survey, if you're interested in that, that will be online, hopefully relatively soon. Yeah, so that's basically all that I wanted to say in terms of introducing or recapping Frank-Wolf. Now what I would like to do in the first step is I would like to give you one example where you can use these methods to recover dynamics from noisy data. And that's joint work with Alejandro Caderera, Christoph Schütte, and Martin Weiser. And the setup that we are considering is the following. You have a physical system that is described by an ODE, so x dot t is equal to f of xt. Xt is here the state of your system. And then usually this function f that describes the evolution of your system here can be written as a linear combination of simpler functions. So if you think back to physics, you might remember all these types of physical laws that you had, and they can typically be written with very few terms. And that is basically these ansatz functions here that you write or use as a linear. You build a linear combination of those. And then what you get is that your dynamic can be basically captured in these ansatz functions, namely that x dot is basically equal to some sparse coefficient matrix here that you see here times the ansatz functions evaluated at the state. And yeah, so that's nothing deep. That has been known for many, many years. And what is interesting, though, is then around 2016, Brunton and al. Realized that you can very nicely phrase this as a sparse recovery problem. And in particular, you can do this component-wise. And you look at it as basically an L2 regression that you have here. And then you have a regularization term where you basically have the where you basically want to keep the support of these coefficients small. There's also other approaches via Gribner basis, but that's not so important right now. And so this problem is hard to solve because you have the L0 norm here, but you can solve it with various approximations. For example, you can do a Rich or Lasso regression and then threshold the coefficients, which is exactly what they proposed in the original paper from 2016. What we did is we followed a slightly different approach that you will see in a second, but before we go there, let me mention that this approach that was proposed in 2016 works extremely well for a wide variety of dynamics. And you basically get also the correct physical model or the governing equation as long as you have a relatively noise-free regime. But as soon as there's noise, what happens is you pick up a lot of additional terms to explain the noise, and then your dynamic is not just inexact, but you just don't have the right physical representation anymore, and then crazy things can happen, as you will see very soon. All right, so yeah, as I mentioned, we looked at this from a slightly different perspective. So we rephrased the whole thing as a lasso problem, where you basically have an L1 ball that you optimize over, and you pick the radius according to the regularization strengths that you would like to have. And we use a specific variant of the Frank-Wolf algorithm, which is called the fully corrective Frank-Wolf algorithm. And the idea is basically identical to the Frank-Wolf algorithm that I've shown you earlier, but rather than following the line segment between xt and the vertex that you have picked up, what you do now is something else. You basically collect all these vertices that you have seen, these are the VTs here, and then you minimize over the convex hull of all these vertices that you have seen. So think of it as a more complicated line search. You now search over the convex hull of all these points that you have picked up before. And that has many advantages. First of all, you don't have the zigzagging behavior that the normal Frank-Wolf algorithm exhibits, but there's a couple more advantages. So first and foremost, you get much better sparsity in terms of the number of vertices that you need to represent the convex combinations of the iterates. Then you have much higher convergence speed per iteration, although the iterations itself are much more costly, and you still remain this projection freeness property that I mentioned earlier. And I'm really hammering on this point because if you have a specially structured feasible region, like a k-sparse polytope, projecting back onto this polytope is highly non-trivial. However, you can solve the linear optimization problem basically for free. Yeah, so a point that is very important to keep in mind here is that sparsity is not only a function of the formulation that you pick, but also the algorithm and the trajectory that the algorithm picks through the loss landscape. That is true in the convex case already because there's many ways of writing your convex combinations, but it becomes in particularly true if you're in the non-convex settings where you have several minimizers potentially. All right, so that's basically the way of how we looked at the problem. And here's an example of what happened. So we looked at the so-called Kuramoto model, which is one of these benchmarking instances for recovering dynamics. So you have 10 weakly coupled oscillators. What you see here is the governing equation. And then what you see on the left is basically the error in log scale in recovery between the two algorithms. So you have Cindy on the right, that's the original one, and then Cindy with C, that's the conditional gradient based one. And as soon as you have picked a radius that is large enough for your regularization, you get a much, much better recovery error with respect to the noise that you see on the x-axis as compared to the other algorithm. But as I mentioned earlier, it's not so much about the recovery error in terms of what the actual loss value is, although it is better. What is more important is what you see on the right. Namely, that is the number of basis functions or ansatz functions that you have picked up to explain your dynamics. And on the left, you see that basically irrespective of the noise level, the number of functions that you pick up is extremely small. It's effectively around the 250, which basically matches what is congruent with the dynamics that you see here. Versus if you look at the original algorithm, the moment you hit a certain noise level, namely about 10 to the minus 6 or 10 to the minus 5, you suddenly start to pick up many extra terms. You see this here in red. There's about 2,000 terms, which are way too much to try to explain the noise that you have in the data. And that's a problem, not just because you have now picked up terms that don't belong to your to the dynamic, but the real problem happens if you use the dynamic now to evolve it over time to simulate the system, which is what you're ultimately interested in. And to make this a bit more descriptive, I have a few innovations for you. So the first one that you see on top is the Kuromoto model that you have seen before. And that's actually for the computation that you have seen there. So now let me tell you what you see. So you see this circle here. The dots are the oscillators, and the green is the true dynamic. So this is the green line, and what these oscillators would be doing is they converge to basically synchronizing with each other across this line. And then you have the black dynamic, which is the one that we have learned with the conditional gradients approach. And then you have the pink dynamic, or the magenta dynamic, which completely diverges after the first few time steps. And that's because you have picked up many additional terms that do not belong into your dynamic. And once you start to evolve the dynamic in time, you have a lot of error accumulation, and the dynamic is basically completely useless. So it matches the trajectory in the very beginning, but as soon as you evolve a bit further, it starts to diverge considerably and has nothing to do with the true dynamic of the system anymore. And that's something that we have observed not just in this Kuromoto model, but in many other models. For example, there's the Fermi Pasta Ulam Chingo model, again, a model with oscillators. You have position, velocity, that's what you see here. Again, the green one is the true dynamic. The black one is the one that you get with conditional gradients. And then you have the pink one here, which basically is the one from the original approach. And you see the same behavior. In the beginning, they all match the same because they solve the same type of problem. But the moment you start to evolve them in time, they start to diverge significantly. And that's due to these extra terms that have nothing to do with the dynamic, and then induce spurious behavior that basically leads to the divergence that you see here once you evolve in time. All right, so that's the example that I would like to present in terms of sparsity and learning dynamics. Now I would like to change gears a bit and talk in the second part about neural network training with stochastic conditional gradients, and that's joint work with Christoph Spiegel and Max Zimmer. So quick recap, stochastic Frank-Wolf algorithm. You don't need to read what is written here. It's the normal Frank-Wolf algorithm that I've shown you in the beginning, except for you not taking exact gradients, but you take either stochastic gradients or mini batch gradients. And if you like, you can add momentum. And then you basically take this as an input to your linear optimization algorithm. Otherwise, it's exactly the same algorithm. As with many of these algorithms, there's hundreds of variants out there. They all have slightly different behavior depending on what you want to do with them. All of them are suitable depending on the task that you look at. And I also don't want to go too much into the details here. What is important is you get all the things that you need to use this for neural network training. In the non-convex stochastic smooth case, you get a 1/√T rate, which is what you would expect to get. It's very fast. You can solve very large data sets here. In fact, we have TensorFlow and PyTorch implementations, and they are, I don't know, a small factor slower than the SGD corresponding ones. And you again remain the projection freeness that you can use to induce solution structure. So what do I mean by solution structure? Rather than giving you some form of theory now, I think it's easier to look at a specific example. What you see here in the graphics is a neural network that we trained on the MNIST dataset. So you want to basically classify digits from 0 to 9, which is what you see in rows here. So the rows are digits from 0 to 9. And the columns, you have different optimizers in feasible regions. The first 4 ones are unconstrained optimizers, SGD, ADAM, ADA-grad, ADA-delta, and RMS prop is a convex combination of some of these. And then in the last 5 columns, you have stochastic Frank-Wolf over various feasible regions. So L1 norm ball, K-sparse polytope, L2 norm ball, L5 norm ball, hypercube, and so on and so forth. And now let me tell you what these colors mean here. So these colors you can think of as positive evidence and negative evidence. So if something is green here, let's say here, I hope you see my mouse, and a pixel is present in that spot in the original image, then this is considered evidence for the class 0. If a pixel is present where something is red, and depending on the strength of the color, that's how strong or the magnitude of the evidence is here, then this is an indicator that is evidence against being the class 0. So the way if I can think of it is you want pixels in green areas and you don't want pixels in red areas in order to match a certain class. And what you can see here is the first standard methods, how we know them. They basically have a very similar type of representation of information in the neural network and how they interpret the data that they see in the image. But at the moment you add feasible regions here for regularization purposes and sparsity purposes, you get a very different picture. So for example, if you take the L1 norm ball, then you see that everything is basically green, and you have also a very sparse type of representation here. If you go to the K-sparse polytope, it's mostly green with a bit of red here.
5 more minutes.
Mm-hmm. And if you then go to the L2 norm ball, then this looks very much similar to what you have seen before and for SGD. And the reason for this is actually quite simple. Namely, SGD with weight decay is basically equivalent to stochastic Frank-Wolf of the L2 norm ball. And that's why these two columns look very much similar. However, then if you go to the L5 norm ball or the hypercube, you see that the behavior of the classifier changes quite dramatically, because now these classifiers are only looking for negative evidence. They look for information based on which they can reject a certain class. And that's a pure effect here that comes from choosing the respective feasible region. And this allows you to basically fine-tune the way of how your classifier works. And you can basically build classifiers that are more like looking for positive evidence and others that might be looking more for negative evidence. All right, so another thing that you can do with these methods in neural network training is when you look at this problem of iterative magnitude pruning. So the idea is here that you want to get very sparse neural networks. And so that I give you just a high level idea here. So you train a neural network to relatively high accuracy. Then you look for all the small weights. You basically prune those weights, you mask them to 0, and you repeat. And there's various ways of doing this. There's variants where you do learning rate rewinding or weight rewinding and fine-tuning. It doesn't matter. These are just different ways of doing this. But at the end of the day, the idea is that you get a very sparse neural network that basically has extremely high test accuracy. And there's a very nice blog post actually by Robert Lange if you want to get a bit of an overview of this topic complex and also more about this idea of the so-called lottery ticket hypothesis, which is closely connected to the idea of pruning. So again, I will not have time to go too much into details, but rather I show you an example. What we did here is we trained neural networks on C410, and then we used two of the well-known pruning approaches, this GSM approach from Ding et al., as well as learning compression from Carrera, Perpinan et al. And we compared this to a stochastic Frank-Wolf variant, where we used the K-sparse polytope as feasible region. And then we basically trained them all to roughly the same test accuracy. And then what you see when you start pruning, the accuracy goes down. And so what the sparsity on the x-axis means is basically how many of the weights you remove. So at 95%, you basically keep 5% of the weights, and you have a 1:20 compression ratio here, so to say. And as you can see, if you throw more information away, of course, the test accuracy goes down. But if you basically build in the goal of pruning afterwards into the training process, but training with updates that are already sparse in and of itself, you see that the degradation in test accuracy here is significantly lower when you start pruning as compared to other methods, because your updates that you used for training were already sparse beforehand. Yeah, so that's ongoing work, and I expect us to have more results on this one pretty soon. And I guess that's all that I had for today. Thank you very much.